So now, today, we are going to be talking about mechanical equilibrium. And it sounds like a really long, difficult word, but it's really not that difficult at all. In fact, you're going to find out when an object that you are trying to solve for is in equilibrium, it just makes the problem so much easier. So we're going to define mechanical equilibrium as when the forces on an object are balanced. And obviously that's going to raise some more questions. What does it mean for them to be balanced? So now we're going to go down here. When the forces on an object are balanced, it means that the net force is 0. Cool. When the net force does not equal 0, then we have something called an unbalanced force. And unbalanced forces, they cause acceleration. So if you have a balanced force, your object is going to just keep on keeping on. If it's not moving, it will stay still. If it is moving at a constant speed in a straight line, it will just keep going in that straight line. So when an object is in equilibrium, it's when the forces on that object are balanced, or in other words, when the net force equals 0. And there are two types of static equilibrium. There's two types of mechanical equilibrium. One is static equilibrium. This is when an object is not moving, in your frame of reference at least. And then we have dynamic equilibrium, and this is when an object is moving at a constant velocity, which means, though, that it's also moving in a straight line, because if you turn, remember, you're changing your velocity. So we are going to look at a couple of different cases for all of these, and then we're going to kind of look at how the math kind of works out. So let's look at the case of something that is in static equilibrium. So we can look at a little ball example that we had from the last lesson. So let's just say there's something just sitting still, your velocity is 0. This is static equilibrium. There's pretty much no other case other than just this. If it's just sitting still, you can assume that then there is no acceleration. So acceleration, equals 0. That the net force is also 0. And this is helpful when you're trying to add up forces or you're trying to solve for other things. You can figure out what the missing force is based on this. Another one we have is dynamic equilibrium. Right, so let's say now this ball is rolling. Right, and it would say it has a constant velocity of, let's just say like 5 meters per second. It doesn't really matter, just giving it a random one. As long as it's moving in a straight line path at a constant velocity of 5 meters per second, this is dynamic equilibrium. Again, acceleration equals 0, F net, your net force, also equals 0. So these two cases, they're actually, depending on your frame of reference, they can be the same case. Because if you're in a moving frame of reference going at 5 meters per second, for example, let's say you have a ball in the car, right? You're going, you could be going like 50 miles an hour, and that ball's also going 50 miles an hour. But if you look out the window, you see something stationary outside. In your frame of reference, it's actually moving whatever your speed is, but in the negative direction. So be very careful about this. I'm not going to try to trick you too much with the whole static versus dynamic, but just know at least these basic ideas. If it's in static equilibrium, acceleration and net force is 0, and the object is not moving in your frame of reference. And for dynamic equilibrium, the same conditions. Acceleration is 0 and F net is 0, and as long as it's moving in a straight line path at a constant velocity. So now we're going to look at kind of what this means. So let's pretend we have so now let's look at the opposite case. What if something is accelerating? So let's say I have a ball. That's a terrible ball. And it gets faster and faster and faster, right? V is not constant. The acceleration is constant. Let's say acceleration is like 1 meter per second. So after 1 second, right, it's moving at a velocity of 1 meter per second. After 2 seconds, it's going velocity of 2 meters per second, and so on. So it's not in dynamic equilibrium, it's moving, so it's not in static equilibrium. So we would also not be able to say the net force is 0. We just actually say the opposite. The net force cannot be 0 if it is accelerating. So I would denote this with not in equilibrium. So if you see these ever, these are like little acronyms, SC, DE, NE. That's what those mean. So now let's look at a category. Let's look at an example. Let's say someone's doing gymnastics. And they're holding onto a little bar here. Right. Can you guess how many forces are on this guy? He's going to be, this guy right here is going to be what we focus on right here. Well, he's got a force on his arms, and he's got a downwards force as well because he has weight. So we're actually now introducing some more forces. We have a tension force, and we'll go over what these really mean a little bit later. And we have a weight force. All you really need to know is tension is the kind of stretchy force. When you pull on something and it doesn't just give away, that force that's resisting that change is tension. And weight is the force due to gravity. So this person's gravity bringing it down. So if I was going to draw a free body diagram, you'd have something like this. We'd have two forces going up, and we have one force going down. Now let's actually give this some numbers. Let's say his weight is 150 newtons, which is really unrealistic. It's like 15 kilograms, which is like 30 pounds. But whatever. Let's say one of the forces going up is 50 newtons, right? What is this other force? If this person is not moving, right, that means our net force equals 0. And this is how this helps us. So if we were, again, starting with the problems we've had before, sum of forces, we would have our, let's say downwards is our positive direction, upwards is our negative. So we'd have our 150 newtons plus our negative 50 newtons plus F. We don't know what F is. But since we know what the net force is, we know it's 0, instead of having to solve for a number here, we could just put 0 there. And now what we want to do is just solve for F. Well, 150 and 50, that's just 100 newtons. And if we want to get 100 to the other side, we just have to subtract 100 from both sides. So we get F equals negative 100 newtons. So notice, by saying that it's negative, right, we know that it's going in our negative direction. It's going upwards. And this makes sense, right? We have 100 newtons. We have our 50 newtons. And those together, right, if we want to get the sum of forces to equal 0, it needs to be 100, because 100 plus a 50 is 150, which is what we have going down. So hopefully you can see how this is kind of useful. If the sum of forces is 0, it makes finding some of these forces much easier. So let's do another one. Let's say we have a box and a bunch of kids trying to push it. I'll draw these really quickly. Right, they're all going in opposite directions. Maybe this side only has 2. Right, let's say each person, so the force of each person equals 30 newtons. Actually, I don't want to do that. So we have 3 people on this side. We have F1, F2, and F3. It doesn't particularly matter which force corresponds to which person. On this side, we have F4 and F5. And we're going to say F5 is a mystery. We don't know. So let's say F1, he's a pretty weak guy. You have 30 newtons. Let's say F2 is 50 newtons. And let's say F3 is 100 newtons. For F4, we'll say it is 125 newtons. Question is, what is F5? So many of you guys can probably just do this in your head. You just added up probably all of this side and subtracted this. And that's totally fine. If you can do that without setting it all up, that's great. But I'm going to go through that kind of a slower process because that process always works, right? So first, we have a free body diagram. Here we have 3 going to the right. 1, 2, 3. They're all different sizes. And we have 2 going this way. I'm not really sure what this other one is. And we have F1, F2, F3. Notice also that my forces are in opposite side of the box that my people are in, right? Because their push causes it to go to the right direction, if in the absence of other forces, that is. So let's just keep that in mind. Sometimes your diagram isn't going to be on the same side as the pictures that you draw. So now if we just set this up, I'm going to denote this as my positive direction. So we have 100 plus 50 plus 30 plus a negative 125 plus our F5. And because the sum of forces on this is 0, and the reason why it's 0, I'm just choosing this situation. I'm saying that this thing is in static equilibrium. Same for up here. If this person is just hanging, it means he's in static equilibrium. So that's just something I chose for the problem. So for you, you'll have to read a problem and try to deduce whether or not it's static equilibrium, dynamic equilibrium, or not at all. So we have this. We add them together, we get 180 here, minus 125. 180 minus 125 is what? 55? 55. Is that right? Let's see. Plus the 5 is 3. Yeah, okay, cool. So now we just move it over and we get F5 equals negative 55 newtons. Again, it's negative denoting and saying that we're moving in the negative direction. So that's how that plays out. Maybe you're wondering about something that's going at a constant velocity. So let's look at a car. So let's say a car is on cruise control. And they're going at a constant 35 meters per second. What is the sum of forces on this? We know that the car has a forward propulsion force due to the gas, essentially. So let's say a force due to the motor, actually. And then let's say that there's also a frictional force. We know that if we let a car in real life slowly stop, or sorry, if we let off the gas, it would slowly come to a halt. That's because of a frictional force. So again, this is a different force that we haven't really discussed much, but you've probably had experience with. It's a force that causes things to stop moving, essentially, in real life. So let's say that this person has to exert a force of 3,000 newtons to maintain this velocity. What is the force of friction if they're going at a constant 35 meters per second? So I'm not even gonna draw a free body diagram. This one's easy. We have that 3,000 Newton force. We have our frictional force. If this is in dynamic equilibrium, which we know it is because I said that we're going at a constant 35 meters per second, we know that the sum of forces equals 0. So then you solve for your frictional force. You get negative 3,000 newtons. So your car that's going at constant speed, it is applying a force, but it's a force that's equal and opposite to the force of the friction. And so many of you may now be wondering what happens if we don't have something in equilibrium. So something that's accelerating. Well, what's going to end up happening is, let's just use this for example. Let's say now we're accelerating this car. Then we don't really know what the net force is, and then we have two variables that we have to solve for. And if this is all the information you have, then you can't solve for it. Later on, we'll talk about mass and acceleration and things like that, and how that factors into the net force. But for now, this is all I really want you to be able to do mathematically with things in mechanical equilibrium.